Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve the following problem. Function f(x), which is square root of x squared plus 1, is defined on the set of real numbers. For natural numbers n, define function f(n)x as follows. The function f(1x) is simply given as f(x), and for all natural numbers n, fn plus 1x is defined as f of fnx. A. Find the general expression for fnx, and B. Using limits, show that as x approaches infinity, the graph of y equals fnx approaches the asymptote y equals x, and as x approaches negative infinity, the graph of y equals fnx approaches the asymptote y equals negative x. Alright, we will get to that later. First, find the general expression for fnx. Here we are going to use the good old find the first few ones and then guess method, which is in fact a surprisingly effective method if you have no clue. So let's find some fnx. First, f1x is obviously given as square root of x squared plus 1. And f2x is given as square root of f1x squared plus 1. And since f1x is square root of x squared plus 1, its squared is just x squared plus 1. So this plus 1, which gives square root of x squared plus 2. And f3x is given as square root of f2x squared plus 1. So square root of x squared plus 2 plus 1, which gives square root of x squared plus 3. And you might have already realized the pattern here. So it is reasonable to guess that fnx equals square root of x squared plus n. But this is merely a guess. So let's verify our guess logically by mathematical induction. For base case, substituting n equals 1 to our guess gives f1x equals square root of x squared plus 1, which is indeed true. Next, assume that fkx is given as square root of x squared plus k for some natural number k. Then fk plus 1x is given as f of fkx, so square root of fkx squared plus 1. So using our assumption, we have square root of x squared plus k plus 1, which gives square root of x squared plus k plus 1. So the expression is true when n equals k plus 1. Therefore, by mathematical induction, for all natural numbers n, fnx is given as square root of x squared plus n. And now the limit and asymptote problem. Here, using limits, we have to show that every fnx has asymptotes y equals x and y equals minus x as x approaches infinity and negative infinity respectively. This seems complicated, but actually it suffices to show that limit of fnx minus x as x approaches infinity equals 0, and the limit of fnx plus x as x approaches negative infinity also equals 0, indicating the asymptotes y equals x and y equals minus x respectively. Here, notice that the limit of fnx minus x as x approaches infinity is equal to limit of square root of x squared plus n minus x. So we multiply square root of x squared plus n plus x at both numerator and denominator, which gives the numerator is x squared plus n minus x squared, and the denominator is square root of x squared plus n plus x. So we have limit of n divided by square root of x squared plus n plus x as x approaches infinity, which equals 0. So we have verified the first asymptote. Similarly, the limit of f(n)x plus x as x approaches negative infinity is given as limit x approaching negative infinity square root of x squared plus n plus x. So this time we multiply square root of x squared plus n minus x at both numerator and denominator. So we have x squared plus n minus x squared divided by square root of x squared plus n minus x. And here, the numerator is n, and in the denominator, since now we have x approaching negative infinity, we write the denominator as square root of x squared plus n, and then plus minus x. And we know that this minus x is positive and approaching positive infinity. So we know that this limit is also 0. Or to make it more clearly in the last part, by letting minus x as t, then this equals limit now t approaching positive infinity n divided by square root of t squared plus n, then plus t, which we can easily notice that it approaches 0. So we have verified the second asymptote. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.